All right, Physics 30s, we are starting Unit C. We are starting electromagnetic radiation. And oh boy, I'm so excited. I love electromagnetic radiation. It's really starting to look into just the weirdness of our universe, and I love it. So let's start with the basics, though, because you need to know what the heck electromagnetic radiation even is. So EMR, electromagnetic radiation, is just any energy that travels in a wave. And this is produced by accelerating charges. We were just talking a lot about accelerating charges and things like that and what happens there. So just a little bit of review from the last unit. Remember, Ørsted figured out what we call the motor effect, and that is that an electric current will produce a magnetic field. Okay, that's Ørsted. Look at him looking all handsome. And then Faraday, this guy right here, figured out the opposite of that. So we call that the generator effect. And that is that a magnetic field can produce an electric current. But of course, we know that when we have a magnetic field producing an electric current, either the magnetic field needs to be moving or the thing that will conduct a current needs to be moving. One of those two needs to be moving in relation to the other. So Maxwell looked at these two things. Maxwell's like such an awesome scientist, by the way. His name should be up there with Einstein and stuff, but for some reason he's not, and people don't know him as well until you really get into things like EMR, and then you start hearing about Maxwell a lot because he was brilliant, just a brilliant scientist. So he looked at this and was like, well, obviously there is a closer relationship here. Because if a changing electric field in space produces a magnetic field, and then, of course, that magnetic field is proportional to the change in the electric field over time, then the changing magnetic field in space produces an electric field. And, of course, that means that our electric field is proportional to the changing magnetic field over time. But this was a bit different. It wasn't just like the electric field around a wire or anything like that. It was just anything in space. If we have a changing electric field in space, there will be a magnetic field in space. So what is this all about? So he said, well, if we have an accelerating particle, what's it going to do? Well, it's going to cause this continuous change of electric fields, which of course then causes a continuous change of magnetic fields, and it varies with time. That is a really big thing that he discovered. So this is what EMR is. It's basically two waves. We have our electric wave. These are the red waves here going in one direction, and then the magnetic wave going in another. Okay? So what's really important is the direction of propagation. A lot of people look at that and say, what the heck is the direction of propagation? That's this C down here. I don't know why it's labeled C. But basically, here's our direction of propagation right there. Okay, so if that is going in that direction, then our electric field, which here is in red, there's our electric field. It's kind of going up and down here like this, right? Will be perpendicular to the direction of propagation, and perpendicular to that would be our magnetic field, which is over here in black. And that's kind of going in and out like this. So they should all be mutually perpendicular, which is really difficult because obviously we are on a two-dimensional plane right here, and I'm trying to explain a three-dimensional thing. So here's what I want you to do. I just want you to pretend that you're right here. Okay? And you're observing what's going on. And so, I'll give you a smile because you're doing physics. Why wouldn't you be smiling when you're doing physics? I don't get it. So here you are looking at this electromagnetic wave. So I want you to imagine that the propagation is going away from you, okay, of this electromagnetic wave. It's going away from you. Then what's happening with the electric and magnetic field? Then, with relation to you, you could see this electric field going up and down. Okay, within relation to you and what you're seeing. Okay, so the propagation is going away from you. the electric field is going up and down, so that means the magnetic field must be going left and right in relation to what you're seeing. Okay, so those are your 3 perpendicular situations. So again, away from you, electric field going up and down, magnetic field going back and forth. And that's how they are mutually perpendicular. And of course, that could be in any situation. The electric field doesn't have to be going up and down. It could be going back and forth. The magnetic field could be going up and down. The propagation could be going to the left, and then your electric field will be going up and down, and your magnetic field will be going in and out of the page, right? As long as they're all mutually perpendicular, okay? And that is how EMR travels when the way the wave propagates. So again, that's basically just the way it's moving is going to be perpendicular to the way the electric field is moving, which is going to be perpendicular to the way that the magnetic field is moving. And that's what you got to know. And of course, then we have our wavelength of EMR. That is this guy down here. There's our wavelength. So again, the distance from one crest to crest, or you could take, this is another wavelength, right? It should be exactly the same for your electric and magnetic fields. So there's your wavelength of the EMR, and depending on that wavelength, we'll have different types of EMR. So Maxwell, he predicted, he kind of looked at this electromagnetic radiation going on here, this wave, the stuff that travels in a wave, and he said, well, this must be light. This must be visible light. Why? Because if something travels in a wave, it has to have all these properties of light, that it reflects, refracts, diffracts, interferes, polarized. Well, you don't know what any of that means yet. And that's why you're here, because you're going to be learning about it with me right now. Well, not right now, but throughout EMR. And so he figured out, oh, well, all EMR must have these same properties because light can reflect, it can refract. Basically, this all has to do with the bending of light. Okay? We know light has to be a wave because it bends in a way that a solid object doesn't, right? Think about water waves. You force water through a small opening and it bends out. So light does the exact same thing. Turn on, when it's dark outside, turn on the light or the light switch in just one bedroom and then open the door crack, and what happens to the light on the dark side of the door? It bends outwards and lights everything up, or lights a lot more up than just like that one slit, right? So that's why Maxwell said that this must be EMR, that light must be EMR, because it's this invisible wave that's traveling, and light does all these things that acts like a wave. So EMR must be light. And he was absolutely correct, but EMR is not just visible light. This is where a guy named Heinrich Hertz came in. He just has a really fun name to say, Heinrich Hertz. So he produced and detected electromagnetic radio waves. Oh, you've probably heard of those before. We're going to go over the entire spectrum really soon, and I'll show you that actually light has a much broader spectrum than just our visible light that we know. So he used spark plugs to accelerate electrons, and then he detected radio waves. Okay, how the heck did he do that? So he had this induction here on this coil, and it produced a really high voltage, okay? And so one side would have been positive and one side would have been negative. So what do the electrons on this side want to do? They want to jump. They want to jump over, but there's this little space here. Well, I drew over the space kind of, so there's this little space here, right? And so the electrons can't just flow, but if you build up enough of a charge, the electrons will jump. That's how we get sparks, right? We know about that. And so the electrons will jump onto the positive terminal. And then what Hertz figured out is when he had this guy at this other guy right over here at the perfect length across, there was also a little spark there. So it'd spark here, and then it would spark there. What the heck is that all about? These are not connected. There's no connection. It's on a wooden table. Like, how the heck does that even work? So what he actually detected was radio waves. If you have this at the perfect length away, then you'll have exactly one perfect wavelength. That doesn't look pretty. Let's do that again. It's gotta look pretty, you guys. There we go. So one perfect wavelength away. And he was able to figure that out because if he moved this any closer, nowhere in between there would it create this spark. But if it's at this perfect distance away, then it created a spark. And that's because this accelerating electron, oh my goodness, over here on this side, was producing a radio wave that propagated, guess what, this way, and went all the way over here and went to this gap right here when there was another spark, because then the electrons are going to want to accelerate over there as well. So figured out, oh, there's these things called radio waves. Well, I don't know if he named them, but basically that's what he discovered there. So this led him to the universal wave equation. You did use this in Physics 20, but now we're going to be using this in context of electromagnetic waves, which are waves now that you can't really see, right? We were talking about waves that you could see in Physics 20, though not all the time. We were talking about sound waves, which you can't see. But anyways, this is our wave equation from Physics 20 if you don't remember, but it's there. It is on your data sheet under waves. You should have already looked at it in Physics 20. And that's the velocity of a wave is equal to its wavelength times its frequency. Speed, of course, is in meters per second. Wavelength is in meters and frequency is in hertz. Just like, the guy that we were just talking about, which is just inverse seconds. Now, we're talking about EMR. EMR is light. So for EMR, the velocity should never change. It should always be c. What does c stand for? C stands for the speed of light, right? C is the speed of EMR, which is light, and it's 3 times 10 to the 8 meters per second. So that leads us to this version of the equation, which this is the only one that's on your data sheet, but obviously for velocity of the speed of light, well, you should just always know that it's constant. It's 3 times 10 to the 8 meters per second. So really, with EMR, our wavelength and frequency are going to change, but our speed is not. A look at this entire spectrum of light that we have discovered. So there's a huge range of electromagnetic waves that vary in size. So all of them are the same in nature though, because they are all produced in some way by accelerating charges, but just accelerating charges in different ways, okay? But that is really important to note. All EMR is produced by accelerating charges. They all travel at the same speed, which of course is c, your speed of light, 3.00 times 10 to the 8 meters per second. That is a constant on your data sheet, by the way. You do not have to memorize that. And they differ only in frequency and wavelength. And that is based on our universal wave equation, because we know that frequency and wavelength are inversely related. So for example, as frequency goes up, what happens to our wavelength? It goes down. And since the speed of light is constant, they're going to go up and down by a constant rate. So there is a direct relationship between frequency and energy. So for example, if frequency goes up, energy goes up. If frequency goes down, energy goes down, okay? And because of this relationship, there's therefore a direct relationship between frequency and the ability of the wave to damage living cells. Doesn't that sound great? So basically, when electromagnetic radiation has a higher frequency, it's going to be more damaging. And that is why when you hear that word radiation, you automatically think of something bad, think of something that can hurt you. There is all types of radiation that is completely fine for you. Visible light is radiation. And it's fine for you. It's not a bad thing whatsoever. It's what enables us to see everything, which is really important. But when we get really, really, really high frequencies of EMR, yes, it becomes very damaging. So that's the type of radiation that you hear about when you hear about atomic bombs and things like that. that's the type of radiation that's really, really bad for you because it's a radiation with a very, very high frequency. So let's go over that big spectrum and see kind of what is what. So I really like this graphic because it's gives you a whole bunch of examples of what it looks like. So let's look at wavelength. So we go from radio waves here, and their wavelengths are pretty long, as you can see. This is in meters here. So their wavelengths can go from anywhere from 10 to the 3, so that's 1,000 meters, to a meter, okay? So our radio waves are usually in there, but they can be really, really long, okay? Radio waves can get longer than that. They can be up to a meter. They can be a little bit smaller than that as well. They can kind of go to here. But radio waves are actually really, really quite big. What are they used for? Of course, they're used for radio. AM radio actually uses longer wavelengths, which is why it can reach farther, but it's not as good of quality. So that's why FM radio uses smaller radio waves, because it's better quality, but it doesn't reach as far. Okay? But here's what I'm talking about, frequency. That's the number of waves per second. So we know it's exactly inverse of the wavelength. So here's your frequency. Okay? So we can see it already starts pretty high, but then it just gets higher as it goes. So frequency is going up as we go to the right. Wavelength is going down as we go to the right, which is perfectly reasonable. Next we have microwaves right here. So microwaves are the waves that are just a bit shorter than radio waves. So obviously this is in order of longest waves to shortest waves, or lowest frequency to highest frequency. That's obviously how microwaves work. Microwaves are definitely a bit smaller, right? So they can have anywhere from like 100 centimeters, not 100 centimeters, that's a meter. Wow. 10 centimeters, 1 centimeter, up to, a millimeter, or a tenth of a millimeter, or something like that, right? So that's microwaves. They have that sort of range there. So other than just microwaves using that, radar is uses microwaves. Then we have infrared, which is of course what detects the heat around you. And that's when our that's when our electromagnetic waves start getting really, really small. Then we have our visible light. This little thing, there you go. That's visible light. In this entire spectrum, that is the light that we can see. So there is a lot more light out there that we can't even see. This is light. This is all light, but this is all that we can see, which is insane. And then we're getting really, really small. So we're down to micrometers, nanometers. That's what we're going to be using for visible light a lot of the time. Okay, and then we get into our ultraviolet, which yes is those damaging rays that come from the sun. So this is when stuff starts to get damaging, is after visible light. So we have our ultraviolet light right here, which yes, over time, if you are exposed to too much UV radiation, that can damage your skin. Then we have X-rays after that, and they're getting real small there. And obviously those are used to see beyond your skin. That's because they can penetrate beyond that, and we'll get into that in a little bit more, which of course, if you are exposed to a lot of X-rays, then yeah, that's really not good for you. And then of course, the rays that everybody thinks about when they think of bad radiation, or the creation of superheroes, but I promise you, gamma rays are probably not going to make you a superhero. Not probably, they're not going to. They're actually just going to damage your cells really, really badly. Exposure just to a little bit of gamma radiation is going to be real bad for you. Okay, so let's go over these in detail. So first we have radio waves. You do need to know these frequencies, by the way, which I know is frustrating, but there's a nice trick to it, I promise. Common source is just oscillating electric current. So you know how on your car you have that like little antenna, right? And what all that's happening there is like you just have an electric current going up and down and up and down and up and down and up and down. And that's how it's creating the radio waves, and it picks up on certain frequencies, and then you tune into that frequency because the radio station is giving off music at that certain frequency of radio waves, and you get radio waves. So there you go. So, of course, as I said, AM radio uses longer wavelengths. So it has better reception than FM, but FM has just a better quality because it's moving on shorter wavelengths. So obviously that's used for communication. And also your TV, well, non-electronic TV now, without Wi-Fi. That's how TV worked as well. So if you have like bunny ears on your TV, it's going to be tuning into a radio wave, if you can believe it. Then we have microwaves, which is 10 to the 8 to 10 to the 12 frequency. Okay, that's the frequency. So remember, frequency. And approximate, like you don't have to get super in depth here. And so that's also created by an oscillating electric current, but we use these ones just because they're kind of shorter. They heat food because all your microwave is doing is heating the water in your food because it makes the water vibrate at a certain frequency that heats it up, right? But radio waves are not going to do that. So that is how your microwave is working, but that's also where our radar and our cell phones work off of. Okay. And when people say, oh no, microwaves are so bad for us, they're really bad for kids, right? Kids do not have as thick of a skull. So if a kid uses a mobile phone, yeah, it's bad. It just radiates into the brain more. Okay. And that's kind of what's happening. And then a 10-year-old, since it has a slightly more thicker skull, then it radiates a little bit less. And then with adults, it radiates even less because we have a thicker skull. And then, of course, our skulls, it will bounce back, right? So it's okay. But when you hear about bad microwave radiation, again, microwaves are not in the bad range of radiation. But cell phones, things like that for really young kids, like, is not great. So you shouldn't have a cell phone until you're a bit older. But it's okay because nobody talks on cell phones anymore anyways, right? All right, and then we have infrared radiation. That's 10 to the 12 to 10 to the 14. So again, this is frequency. Let's take a look at these exponents. So we got 4 to 8 for radio. We got 8 to 12 for microwaves. So look, what's it going up by? This is going up by 4. This is going up by 4. This is 12 to 14, this is going up by 2. So now every single one of the exponents will always go up by 2. So if you know the order of EMR, radio waves, microwaves, infrared, so on and so forth, then you know the first 2 is 10 to the 4 to 10 to the 8, 10 to the 8, 10 to the 12. So those 2 exponents go up by 4, and now all the rest go up by 2. So I'll keep pointing that out. Infrared radiation. So before we had oscillating electric current, it was like going up and down, but in a way that we could still kind of see. Now this is just vibration, right? A lot of the time we kind of put it like that. But obviously we know that because that's what creates heat, is when molecules vibrate back and forth, they are hotter. So that's what's going on. So obviously used in heat lamps, but we've also created the technology to be able to read infrared radiation. So this is an example of an elephant and it's infrared radiation that it's giving off. So apparently they're really, really warm in the trunk and have really, really cold ears. Oh, poor cold ears. So that's infrared radiation. And then of course we have visible light. So that frequency goes from 10 to the 14 to the 10 to the 16. So again, if you remember that radio waves start at 10 to the 4, and the first 2 go up by 4, and the rest go up by 2, you should be good. So this is due to a transition of electrons and atoms. That is still an accelerating charge. So if you have your nucleus there, and then you have all your energy levels, looking real pretty. And then we have an electron here at an upper energy level and it jumps down. It actually lets off EMR in the form of visible light. So that is actually how visible light is created. It's just electrons jumping down energy levels, which is insane. And so this, of course, is just detected by our eyes, and we are able to see this. So here's our range of visible light. It goes from red to violet. So what I need you guys to know is that red will have a larger wavelength, but therefore a smaller frequency. And of course, violet light will have a smaller wavelength and a larger frequency. Okay, and you will actually also need to know the range of visible light. Okay, it goes from approximately 750 nanometers until 400 nanometers approximately. Okay, and this is later in the notes, but that's also something that you're going to need to know about that. Okay. Next, we have ultraviolet radiation. This is your UV rays. Obviously, you have heard of these before as well. These are what are given off from the sun. This is also due to transmission of electrons and atoms. But if the transmission is such a big energy jump, then it could be letting off UV radiation instead of visible light. Okay, so this goes from 10 to 16 to 10 to the 18 for frequency. That's hertz, of course. So like I said, they're all going up by 2 now. And of course, this is detected by our skin. Okay, but it can also be used for something useful, and that's aircraft component testing. I don't know how they do it, but they do it. That's awesome. So UV, of course, there are different types of UV rays, UVA, UVB, and of course that they are defined by how much energy they have. UVA rays have much more energy than UVB rays, and so therefore they have much more penetrating ability. So we definitely need protection against those UVA rays. Absolutely, but UVB also really good. Then we have our X-rays. So the frequency here goes from 10 to the 18 to 10 to the 20 hertz. And these are created by rapid deceleration of electrons hitting a target. Okay, so here I have an X-ray, and we have this heated filament over here, and it emits electrons, and then the electrons are going across here, and they hit this barrier here, and obviously very, very rapidly slow down, and X-rays are given off. So obviously we can use, what just happened? Obviously we can use these for medical diagnoses, and it's okay to be exposed to X-ray radiation every once in a while. So basically just keep in mind, as it goes on, as the frequency gets bigger and bigger, that's when even a little bit of radiation is going to be really bad for you. But when we're talking about UV obviously takes a really long time and a lot of exposure to really damage your skin. Here, it's definitely less exposure, which is why you definitely are going to see an X-ray technician go behind a lead barrier every single time. That's because if they were exposed to X-rays multiple times a day, every day, yeah, they're going to be sick pretty soon. Like, it's really not going to be good for them. But for you to have an X-ray every once in a while, I don't know how often you guys have X-rays. It's probably not that often. It's not a problem whatsoever. Okay? But again, continuous exposure to X-rays is going to be real bad for you. So that's why the X-ray technician has to go behind the wall, because they're doing that all day. They can't be constantly exposed to X-rays. That would be very, very bad for them. Okay, so give your poor X-ray technician a break. So X-rays, basically, they will penetrate more into thinner places, right? And less into thicker places, so they're really able to see bone quite well. Okay, in less dense places. So that's what's going on there. So finally we have gamma rays, and no, they will not turn you into the Hulk. So please, you do not want exposure to gamma rays whatsoever, like even a little bit. Just a little bit of exposure to gamma rays is going to, well, not kill you right away, but it's going to cause a lot of complications. It's really not going to be good. So don't do it. So when we're looking at the frequency of gamma rays, we're 10 to the 20 to 10 to the 22. And this is due to the complete decay of a nucleus. And we're going to go over nuclear decay a little bit more in the next unit. But a nucleus decays, it gives off gamma radiation. So that's like nuclear fission, basically. When that happens, you get gamma radiation, and it's real bad for you. Okay? But we can still use this in some sort of a good way. We just have to be really careful with how we use it. But it can be used for medical diagnoses, okay? And it can also be used for food sterilization, which is pretty important. Like, if you don't have a lot of food and you need to sterilize food, well, you expose it to gamma radiation, it's going to kill all the bad cells in there. So there you go. It also is used, you'll hear of radiation therapy in cancer patients. And that's just because it can be used to destroy the bad cells, which is awesome. The only problem is it sometimes destroys some of the good cells along with the bad cells, and then you hear about things like radiation sickness. Okay, so what do you need to know? Let's take a look at these frequencies again. So again, 10 to the 4, 10 to the 8, 10 to the 8, 10 to the 12, going up by 4s. Now it'll go up by 2. 12 to 14, 14 to 16, 16 to 18, 18 to 20, and finally 20 to 22. So ranges from 10 to the 4 all the way up to 10 to the 22. Okay, first you go up by 4, then the rest go up by 2, and that's what you got to know. Visible light, as I said before, goes from 400 nanometers to 700 nanometers, where the 400 is your violet, and the 750 is your red. Okay, and of course, you only need to know the basics. Like if I said, what color is likely to happen at 450 nanometers, you should be able to say violet or blue or somewhere in there. Okay, and of course you know the spectrum because you've been learning it since like kindergarten, and that's of course Roy G. Biv. So our violet is at 450, our red is at 400, and our red is at 700 nanometers. And then of course white light is the reflection of all those frequencies all together, and black light is the absorption of all those frequencies all together. And that's it. You can stop listening to me. I've been talking a lot today, so good luck. Hope that made a lot of sense. I promise it's going to be a fun unit. I'm really excited.